and do a nodal constraint and fix that point there. So that would be that point right there. Click on it, 1,000. There's 2 points there. Make sure you're changing 1,000 and not 1,001. Make sense? No, we deleted the element 91. That was a large mass.
So what do we do?
He's not going to let you delete the node.
Whatever I deleted.
What's that? You can come back over here and it should say one element deleted.
Mm-hmm.
Yeah, so that's that would. So it looked like a you know, when you click on it, it looks like a center mass symbol. It's kind of like this. Center mass symbol. Big purple blob. Okay, so let's go ahead and fix that point. Say okay. Override yes. Control G. Okay, so we want to put the excitation right there, right? So let's go ahead and bring those excitations in. Okay, so if you notice there's some what I call earthquake files. This is the Northridge earthquake from actually really close to Northridge, apartment structure. So we're going to say file, import, analysis model. Hit okay. And if you go somewhere where that file is, where we put it,
The transient file?
right there, yeah. So wherever it is, it's going to be earthquake1.dat, and then import, earthquake2.dat, and earthquake3.dat.
All three?
All three. You can do one at a time though.
Oh.
That's to do one, then the other, then the other. And hopefully it says no errors when it updates.
Earthquake 1, 2, and 3.
Yes.
Yes, but one at a time. There's earthquake1.dat, earthquake2.dat. So these are in mass gen format.
Who's on there?
No, I'm looking for it.
We'll say import, analysis model. And then okay. And search for those files. Wherever you put it.
There is a zip file. It's a zip file of one color.
Oh, if it's zip, you really need to unzip them. Yeah, you really need to unzip them. Did you unzip them?
I just drag and drop.
What's that?
I drag and drop it.
Oh, okay. So you unzip it that way?
Yeah.
Yeah, because this is a recognized zip file. So you make sure that you can drag and drop it or unzip it or whatever, right? It's gotta be in its native form.
We're inputting earthquake 1, 2, and 3, or?
Yeah, 1, 2, 3, make sure it's a .dat, because that's the standard mass gen format. Remember the format we looked at? Field 1 blank, 1 through 8 is small field format, and then field 9 is blank continuation. Anyone zip it?
Well, it's in your download with transient.zip, and then you go to file import.
Nothing you do is just go ahead, right click and say unzip
Yeah.
files.
If it's in the zip file, you can just like drag and drop like this and then open it.
You don't use zip files? How could anybody not use zip files?
Yeah, I don't know about that.
It's like mandatory knowledge.
You know, one at a time.
Okay, while you're waiting then, I want you to do this. Go ahead and, once you want to close these ones up outside for a second, so close all that stuff up. Close up the other one, yeah, perfect, one more. And then go to your graph, your chart. So go across the top and you'll see, perfect, see the chart there? And we're gonna create a new one. And I want you to click on the X, Y. Here, yeah. And say new data series. And I want you to go to where it says type.
Yeah, where's the graph and chart?
That, a little to the right. One more
I'll
over.
do it again. Okay,
Oh,
everybody have
and
the
then
chart
X,
up?
Y.
We're gonna get you like a laser pointer.
Chart is on the left. All the way on the left.
Our lightsaber.
Everybody have the chart?
Look at both right corner.
I have chart data series, right? That's what
It
we're.
all says it's like that chart. Non-union. That makes sense? Everybody got that?
Yes.
And then it's gonna have something right, so the very right side of that called the XY. Click on that. Make sense?
Yes.
And then say new series, okay? Everybody got that?
Yes.
But they said no, Kirby, no.
I heard it from over there.
It's the echo.
Maybe it wasn't
Got it?
email, I guess.
Chart, open chart.
I heard it from everybody.
I didn't hear it at all.
It's on Reddit.
Where's your chart?
Nope, never saw it.
Good, click on that next
And I
one.
think it's on the website. But yeah, no email looks like.
New series.
Unless I deleted it.
I'll go talk to Ed.
And then change
Just maybe I'll have to go
type
talk to them, that's all.
function. So
Probably
change the
make it
type to
bigger.
function, and you can see those are the files we use
Whoa,
for.
missed it.
Oh no.
Does that make sense?
Once again,
I think he said which one do we click over there?
function, okay.
So to a function,
Okay,
right?
Yeah.
And then it's gonna bring up the functions that you just have to look. If you wanna look at any functions, click on it. You wanna look at all three functions, you can put them all. Let's just put one, otherwise, I just put the first one on, this is gonna be we call it the east-west horizontal. Say okay.
East-west horizontal.
What's that?
whoa.
What's that mean? East-west horizontal?
Yeah, so the horizontal, east-west. The north, north-south. So it's vertical. What happened to our series? You can all three if you want, but you see what's gonna happen, it's gonna override it, right? So anyway, I want you to go to the top under the symbols. You can turn the symbols off if you want. You can actually right now, it's like remember right now, so right now, so.
Once we've imported that data, we can't.
What's it, yeah, you just go ahead and say right now, so you right now, so you and sure, and say marker settings, or display markers. I find the charting to be a little bit different than the rest of it because it added so late in the game. So if you say right now, so they turn markers off. So that is that's east-west telegram in terms of G's for the Northridge earthquake. I think it was what, 76?
So this is the actual data from.
This is actually data from
Seismic, like,
right, this is from USGS.
okay.
So you can go to USGS and download pretty much any earthquake that we have for, I don't know, for years, right? We've been recording data since the first one recorded was really the one down there in North Central, the most famous one we first recorded. It's used for years and years, that was what, I don't know, 20s or 30s. But now we have pretty much every time there's an earthquake of any significant magnitude, we record all the data, and then they correct it for instrumentation error, and then they put it on the web. And it has like 20, it has center format, has 50 lines, header format, which tells you all the data, helps collect where it is, the azimuth location, etc. And you can download that, use it, that's this.
So does this come as like an Excel file or?
It comes in a text file, a CSV file, CSV file.
And then how do we import it to,
I have a program which converts it over to an extra file.
does it help me?
But no, you can, instead of having that, you can go to functions and import it in the function also.
Okay.
But it's a little more work than just the long. But yeah, if you play around and see, go to functions and say import file, what you need to do though, if you do that, you probably need to Excel, go to Excel, clean up the header, and then put it into a single file format.
Okay.
Or actually a 2-column format.
One would be a time.
Time would be a time, I remember, it was awesome to download. They're almost always, they're all digitized to 50 hertz. So the delta T of 0.05, or 02, I'm sorry. So that's the standard because they're like a very frequency, right? They want to digitize it any higher, that's the same. Plus, there's thousands. Every time there's an earthquake. Wow. You can download it from almost anywhere in the world, right? So you can actually see it's very common for an earthquake. You have to build up the rumbling, right? Low frequency stuff that comes from Q wave. It's the building that large acceleration, and you have a taper off. So this is time, 60-second track, 60-second thing. But really, we're only going to run it out to 10 seconds, maybe 20 seconds, maybe.
You get like the magnitude better from this chart?
Yeah. Well, as far as the
Like a 6.0,
no,
9 point, whatever.
no, you can't. Because this is local, because depending what you recorded, if this is, if this was like 40 miles from the earthquake, that'd be like a magnitude 10 hypercon destroyer. But this was very close to the epicenter. So without calculating the distance, effective distance, the epicenter.
What is that?
And then the
It
magnitude.
says that in order to
You have no idea.
you can get it as a graduating senior, but you have to apply before registration.
Missouri earthquake, right? We'll record that here.
I just remember October 9th, and I saw it somewhere, and I did it like over a week ago.
I didn't see it.
Well, I also went to an advisory, and they told me to do it right away.
No, that was gonna, then we can count back.
That was
out
my bad.
the magnitude. The bottom line is no.
Is there like a local magnitude? Look at, from this side of the graph, you tell how hard it was shaking
No. We can tell how hard it's shaking
at that.
at that location, yeah. But you can't relate that to the earthquake magnitude.
Right, so how does that translate from like 0.6?
0.6 Gs.
Okay.
0.6, that's Gs. Those are all, everything's normalized into Gs.
Okay.
Because no matter where you go in the world, metric English, everybody knows what a G is.
Mm-hmm.
Right? So basically, this is the, half a G. So that's a lot. Half a G acceleration is a lot for building to do. And you gotta remember, this was recorded real close to the parking structure that collapsed in Northridge. So let's bring up the vertical, which is actually very surprising about this. We'll bring the vertical up. So that would be the last one in the data series. And we can actually put this maybe on top of the other one. Okay, let's just do the last one. Okay. Okay.
The last one, 3?
3, yeah. And then, so you look at the vertical. Markers up. That's pretty significant, right? That was a very unusual earthquake, though. We typically don't have that much vertical motion on an earthquake close to the epicenter. It's very unusual to have one. There were people that they said, because you're getting about a magnitude of people, almost 0.8 Gs, right? There were people that they said they were in bed that would have to hit the ceiling from the earthquake. They were really close to the epicenter. Wow.
That's another question.
Yeah.
The vertical is kind of, I hope it's self-explanatory. Going up, that's the upward acceleration.
Yes, I believe so. I'm not positive, but I believe that is.
And then what about, like, this was the first one we uploaded was east to west?
East-west.
How can you tell which side?
I'm just looking at the header, because it may not be exactly east-west either, right? This would be east-west, but it could be like 85 degrees. The header will tell you exactly. Yeah, all the information. It also tells you how the data reduction, the error correction. There's a lot of information. Matter of fact, I think by the time I actually have USGS. But this is pretty significant vertical, right? And I think that's, normally we consider the vertical maybe around half and a half vertical to the horizontal. But in this case, it was pretty long. Anyway, so that was just to show you actually did import it. Now what we're going to do is we're going to now apply this to the base. We'll apply all 3 of them, X, Y, and Z, to the location below the springs, which would be the soil movement. Does that make sense? Yes, sir.
How does Nastran know that this is acceleration?
It doesn't. It has no idea it's acceleration.
So how does it take that data?
It's just raw data. I wrote it. I brought it in. It's not. Now we have to tell it what it is, right? It's a matter of, if you look at it, it's just called Nastran Table D1. So a table D1, is a generic format, time, it doesn't have to be evenly spaced, time, value, time, value, time, value. That could be a displacement, it could be a velocity, it could be almost anything, you know, typically in the time domain, typically. Even though it's in the time domain, so time, value, time, value. Makes sense? But we're gonna tell it it's an acceleration. Later on. So let's go ahead and close that guide, it's kind of cool. Now let's go ahead and see if we can get this thing to work. So go ahead and save this because that's a lot of data there. And I'm thinking if we run this thing out for say 15 seconds, the only reason I want to not normally run it out for all 60 seconds, it'd be kind of cool to see it, but these things are very limited, a lot of resources that it takes to run it. So the more time steps you have, the more resources. I don't think we can run much more, about 10, 15 seconds. So if we do 15 seconds, right, and we digitize and we have an execution of delta t of 0.02, that's 50 hertz, right? So the number of time steps would be 50 times 15, 750 time steps. Make sense? So we're gonna run 750 time steps with the delta t of 0.02 seconds. Does that make sense? It should run pretty quick, but that's not that many time steps. More worried about the car. The car's a much bigger ball. So let's go ahead now, and we got the constraints on there, that's good. Let's go ahead and put the load on there. Let's see if we can run it. So we're gonna say model, load, nodal, give it a name. Cool. Select that middle point, 1000. Perfect, that's 1000, not 1001, right? Say, okay, now, this is in terms of G, which is not consistent, right, with our model. Our model's in terms of inches, correct? The conversion from G to inches per second squared is? Correct?
344.
386.4.
Yeah, 376.4.
Yeah, something like that. I think that's what I heard. I copied him, so.
Cool. So let's go ahead and put in 386.4 for the value. Oh, let's first of all do acceleration. So we have acceleration, and then the value in the x direction is 386.4. And the time is going to be equal to table D1. One table D1. One table D1. Cool. And say okay.
Okay.
That makes sense? Let's go ahead and put the other two in also, you gotta be separate, because they all have different functions, right? They all have the same dependency, we could, the same exact profile, then we could make them, one file, but they're all different profiles. So let's go ahead and do it again, 1000.
Acceleration.
Okay. Acceleration, 386.4 in the y direction, nope, not y direction, the x direction. Y direction, 386.4. The time dependency 2, table D1. And then finally, the last one is going to be 386.4. Time dependency of the earthquake. This makes sense, everybody?
Yep.
Cool. That's it. So those are going to be our three inputs.
Oh, look at that. So, go ahead, that is the direction.
Yep. Pretty awesome. Okay, so now I think we're almost ready to run this guy. Now we could go through, and we're going to do this anyway because it's going standard. So let's go to. If for some reason the link doesn't seem to be really great, this we're going to probably redo it when we actually export it. So we'll go ahead and say model, load, dynamic analysis, and if you look across the top, again, for some reason it doesn't really seem to save this very well. I don't know what I'm doing wrong, but most of the time I hardly ever go through the menus for dynamic analysis. I'm almost always typing in my hand because all the options. But there's two types of transient analysis that we can do. Modal analysis, modal transient, which basically what we do is we find the mode, and then we do transient analysis on the mode, and we use the mode from modal space back to physical space. We'll talk about that later. We're not gonna do that, we're actually gonna do this one over here called the direct transient. And direct transient is solving in the time domain, the physical degrees of freedom in the time domain, using a central difference approximation. And which you will see towards the end. It just steps through time, one step at a time. And determines based on where you are now whether the next time something using something different. So we're gonna put an overall structural coefficient of 0.05. Give us some structural damping. We're gonna do a conversion into, and again, this is probably more than we want to get into, but this converts it from a viscous damper to a direct transient damper. Put in 5 hertz, or put in 2 hertz, I'm sorry. That's the first one. That one will be blank. And number of time steps, we're going to do 750 time steps. The delta T is going to be 0.02. And we're going to output every single one, we're going to output every time step. So make it 1. Now what's going to happen is I don't remember any of this. I don't know why. Is that okay? I think it's ready to run. Let's go ahead and say file. Save it? Yeah, save it, yeah, definitely save it. Okay, export. Analysis model. If you actually try running it at this point, you'll get an error. And say edit, create edit. And then say delete that guy. Let's go over run, delete. Okay. And then say new. In the statics, we're going to go to transient dynamic. And say next. I'm going to go slow, make sure you all get this. Everybody have that? Okay. So should I start again?
Yeah, I think we're
Okay, go
good.
ahead and cancel it again. So first of all, let's stop right there. Do everybody bring up that menu? Okay, start from the beginning. Cancel that guy.
Create, edit, set, Arturo. Create, edit, set, Arturo. Delete. Delete.
Okay.
Are you
Got
good?
it? Okay, right there.
Yeah.
Cool. Say new.
I'll get him.
I'll give it a name if you want to, but we're gonna run transient dynamics. Awesome. Next. Okay, there's nothing here. Say next. Nothing here. We're next. Got all defaults. Next. Next.
Next.
Okay, let's stop right there. Everybody right there? So, did everybody say direct transient solution on here? So they did pick that up. And then I think that's it. And next. Okay, so but it doesn't pick this up or something. I don't know why.
Well, it says use load set options on the top. Can we hit that?
What's that?
It says use load set options on the top. If we click,
You click on it, see what happens.
nope. Well, it might. I don't know.
Yeah, that may work.
Might.
It might work.
Arturo,
Let's try that next
please try
time.
it.
Try it next time.
All right.
Yeah, I think you're right. I think that's what you have to
Okay.
do. So in the meantime, let's
I'll
just
fucking
put it
do
in
it. I don't
here.
care.
This would be
0.05.
0.05, I think I said.
Yep.
And I think I said
2
hertz for W3.
Nothing.
And I
750.
think I said
0.02.
0.02,
One.
and 1. So I bet you're right. I bet you if I said low type.
Oh yeah.
Gotta try it next time.
Yeah. I mean, I can try it right now if you want.
Sure, go ahead.
All right. I risk it to get the biscuit.
And then say next. Yeah.
For the damping coefficients, are those like just
Which
like
one?
the damping coefficients, like the standard damping? Is that like a standard number from 0.05? Is that like a normal?
Well, okay, what that is, you take, I think I took my basis, but anyway, in viscous dampers, we specify viscous damper by 3 different methods. Q factor, theta, which is going to be critical damping ratio, right? And then G. G is referred more to structural damping, and G is equal to theta. But the problem is, to get to, viscous damping has the modal response, right? So we have to convert that to a direct transient. So we convert this viscous damping to a damping matrix C, instead of viscous damper, matrix C. But it has to have a conversion frequency to do that. And that's what the W3 is, the conversion frequency to achieve a suction damper. And typically we pick up the first mode. And the first mode is around 2 hertz. That's what. It's not exactly close enough. Okay. I know it's not a very good answer, but without getting into a lot of the math, it's good enough. How's that sound?
Nice.
Okay, next. I think we're okay now. Next. I think everything's next. I think everything's okay. Yeah, I'm gonna say okay, and then say analyze. Very good. You got fingers crossed? Make sure you didn't screw up on this guy. So far, so good. Oh, good, it's run. It's done. So what it's doing now is outputting the results. It's actually reading the results. So read 751, we can run from 0 to 750, right? It's 751, right? 761?
Wow.
Really?
You probably put 760 instead of
Maybe it's
750.
hung up on something. Does anybody else have 761?
Well, you might be able to change it. Hit Alt F4 real quick.
Don't do anything until it,
Hit Alt F4.
Oh, I just did it, dude.
Oh, I did it. Ruin it, man. Alt F4. That's how you go back.
Fix everything.
What did she used to say?
That's fine.
What the way you got? That's weird.
Maybe he typed in 760 instead
So
of
maybe he typed in 761. Of course, that would be the same here. So we're gonna animate multi-set. Multi-set because each one of these is solutions. Each solution is like a static solution. So we have like 750 static solutions. And so that's called a multi-set. So we're in multi-set.
You're telling it to run all three of them.
All three of them, yes. And make sure it starts on, click on the side over here. Make sure it starts on, oh no, right here, where it says case 1. Yeah. Over there you go. And then scroll up, make sure it starts on the first case, line 0. If you leave everything blank after that, it's gonna assume that you want the whole type history. If for some reason you only wanna do a small set, you put a final in, and just go, just show you the part that you want. Start at 0, leave that blank, and do the whole time history. Make sense? So, okay.
Do a double translation, all that's fine.
Yeah, I don't think we asked for suggestions, so yeah.
Yeah, I played and paid for it.
We could ask for
Like
suggestions.
over a week ago. Whoa!
Whoa.
So that's the building in the earthquake.
Whoa.
Now, of course, it's scaled up, remember that. But, building about 26 inches.
Jeez Louise.
Which isn't, it's a lot, but if you were in that building, you'd feel it.
Mine's only moving 19 inches.
Really?
Ah.
There's a 26.
Is it criteria content? Whoa! Wait. Whoa!
Super wiggly.
Oh, it's just, sorry, over again.
Whoa! Whoa!
Kind of getting ready,
Whoa.
get ready, the chair. But no, this is very low frequency, but again, we exaggerated this tremendously.
Whoa.
It wouldn't really be that much because we put some really soft springs in, right? And I want to show you the soft springs. You see, this is the base of the building here, and that's the thing. You actually see the springs stretching.
Yeah, mine's definitely not 26 inches, so I hit that load set thing, and mine's
Yes.
huge. So look at that.
Yeah,
Yeah, so that I don't think that works.
what's going on with that? I'm gonna play with that. But yeah, that number's huge. I don't understand that at all.
15,000 inches.
Yeah.
Nice.
That's a lot of inches.
But very flexible.
I'll hit all at 4. It'll probably fix it.
Yeah, it work.
Anyway, pretty cool, huh? I think it might, you know, if you tighten up those, springs to make it more realistic, it'd be a lot less than that. It would be a lot less.
I hit 26.
Matter of fact, the base would be originally attached to whatever this guy's moving. That's
I hit 26.
What material do you make? I think, building
I
out?
started off at
the building
19.9.
steel.
PLA.
I think a lot of inspections, especially
Toothpicks.
the appears to be blocking and stuff,
Toothpicks and marshmallows.
is basically due to the springs and things.
Okay, let's try this.
In some locations, that's pretty realistic, right? So if you're bending your lot of
650.
sand,
No, 750.
it could
750.
be that.
Alright.
That one's
Okay,
If you're
what up?
one on bed lot, it's pretty much the same, exactly same. Or loose soil would be very soft. Anyway, that's what we call transient analysis.
Oh, see, that only did 343.
Whoa.
And we
Oh, there it goes. Oh!
It's still going. Why are you going 1,000?
Alright.
Did you take out the
Go
outputs
ahead
from the
and save
previous
that.
one?
What went
Did you
wrong
delete
with
the
that?
outputs?
Yeah.
Delete the outputs.
I deleted the entire.
You're also restarting it.
So bring up the car, and what we're gonna do is, we're not gonna put the suspension on it right away. We're gonna assume the suspension's in, they stop, depending on how much time we have. Maybe for the homework, you can do the suspension.
What?
Import?
What homework?
Yeah, go ahead and import the neutral file.
Oh, fudge. It's still saving.
No, we're done with the building. Go ahead and close the building up.
750, 0.021.
Yeah.
Okay, so like I said, if you look at that building, if you look at the car, excuse me, it's one that's made up for another class.
Advanced FEA.
So the cool thing about the neutral file is that unlike all the other programs like, you know, MathCAD and SolidWorks, you know, if you have like the SolidWorks 2019, there's absolutely no way you can open it in 2018,
Whoa.
right? You can always save it as a step file or an ISIS file and bring it in, but then you lose all the parametrics.
We're still not getting
It's
there.
very unfortunate the way they do that,
Really?
they're going back there. However, that's not the case here, so if for some reason
You guys
you want to
have
open this file in an old version, you save it as a neutral file, with the neutral file version number, like you got your saved as
criteria?
neutral file 12. and you
All
can
that
save it by,
for.
you know, 5 years.
Look at it
So
dance.
save it as a neutral file, and open it up as a neutral file, and it'll automatically convert it to a. I guess they say neutral. Okay, so if you look at this guy, I want you to zoom in on this guy. Doesn't matter. You zoom in and rotate it around a little bit so you can actually look at that. So you can see this is this is nothing more than basically a large mass here, I think. We can get rid of that. I'm not sure there's a mass there now. And then that's anyway, the rigid element, that's independent point, very constrained to my frame. And this is just like the shell of the body, it doesn't represent any real car. You know, I just picked something up. So what I did is I picked the car up and I meshed it, and then I threw away underneath the carriage, so to flip it over. I didn't like the way they, I wanted the frame going right down the side like we typically have.
You didn't model this. Oh. How did you model it?
I made a SolidWorks model of the body. Then I imported geometry. Then I auto meshed the whole thing. And then you flip it over?
Yeah.
And then I removed the bottom and put my frame in and then did the bottom. That way, otherwise this wasn't nice like that. And then I extruded these out to get that. Most of the stuff I do, I do most of my work in solid modeling, and I do it on modification. Take advantage of what you can. Whatever's the most efficient way of doing it. So what we're gonna do is we're gonna do something very simple to you. And we are going to, these, let's see, can you say let's say delete model element, Yeah, oops. Now, it looks to me like maybe, no. Okay, so there's no, oh, it's past there, okay, that's good. You can click. Let's go ahead and do the same thing we did on the previous one. We're going to assume now, instead of having a acceleration now, we're gonna have this go over a bump on one side. So you're driving over there, right, and see a bump, and you go decide to go one, only one type is the bump. So, we're gonna do a little math here. Very little. So here's our bump. Here's, first of all, if I look at my wheels, there's a wheel well, right? So there's my wheels, and the distance of the wheels here is going to be 18 feet, which is a pretty big car.
This is a really long car.
That's a long.
It's like a truck.
And it's going to go over a bump. This one first, and that one first. It's moving at 20 miles an hour. Right? Going over the bump, and the bump is going over, it's like this, the height of the bump is 6 inches. Spacing on the bump is 18 inches. That's a pretty good speed, 20 miles an hour. Does that make sense?
You're going over the curve.
That's really cool. We had, when I worked at Hughes, we call it the mini Munson track, which is the same as we have back in Avenue Proving Grounds. So they have like several bumps that we take it over. Back then, I think there were M10 trucks. I don't have those anymore. But anyway, we mounted radars on around there, and so they're 10-ton trucks. And we had what called, there was the Belgian block, which is like, we had the washboard, which is like this, and then we had the radio washboard, which is probably the worst. It went like this, but it was on a curve like this. And it was really cool because when they would take that, it would make 5 miles an hour. But sometimes they took it a little fast, right, like 10 miles an hour. And actually, with bouncing, you actually see the truck go up like this and go like 2 feet off the ground to the side and bounce back in the car. It's a simulate, it's the field, I suppose, simulate. Anyway, we always had some videos of all that. All that stuff like lead on it. A lot of fun stuff. So anyway, so at 20 miles an hour, we can't really work in miles per hour. We really have to work in inches per second, right? To be consistent. So if we take 20 miles an hour times how many feet in a mile? 5,280, right? 12 inches. 12 inches to a foot. And then divide that by number of seconds. That's 3600, number of seconds per hour. That should give us a speed and velocity of, I calculated here, 352 inches per second. So, for that to go 18 inches at 352, if I take 18 inches and divide it by the speed of 352, that pulse duration is going to be equal to 0.051. Does that make sense? Very good. Also, I can search the pictures on there. So I did that. I did the Bay Bridge test. No, there's the King's Bridge. Really amazing. They called me up and said, we test the bridge. Some of the things was short here. But the bottom line is we want to excite the bridge. The bridge is about 3 times the size of Prince Thomas Bridge. So I made up some ramps, 6 inches high, and then we loaded up 2 trucks with maximum capacity of about 105,000 pounds. I think I just figured out how to do this. Drop the truck on the bridge, right? So
I think we're pretty much there already.
2 miles an hour.
Because we're generating it with equations.
Okay, now it's 4 miles an hour. Bam. 5 miles an hour,
We've
the
used it
truck
now.
flipped off the bridge. It's about 18 inches high, 110,000 pounds. It was actually a transporter grabbed what it was. And we said, okay, now go to 6 miles an hour. The guy says, ain't no way. I said, well, go to 10. He goes, yeah, not by me. Because 6 miles an hour, 5 miles an hour, he was up about 18 inches off the ground. He kind of had fun. Not very often. So anyway, so 0.05 seconds, 0.51 seconds. Okay. So that's one part. The other part is, so if it's 0.015 seconds time, then in terms of the sine wave then would look like that, wouldn't it? We only do half a sine, but the sine would be like that, right? So the period of the sine wave, well, that going over the bump as input would be equal to 2 times the half sine. So the period is equal to 0.102 seconds. That would be the period, correct? Does that make sense? Now to convert that into radians, we don't really, normally we convert to radians, but the input on VMAT works in degrees, not radians. So the formula would actually be then equal to 1 over t, that would be F is equal to 1 over t, right? So to get that in terms of degrees, we multiply that 1 times 360. Does that make sense? So then the equation for that would be the sine of 1 over t times 360 for degrees, not radians, times t. That would be the equation, correct? And how long does that pulse last? It lasts 0.051 seconds. Does that make sense to everybody? Any questions at all? This is how we do it. So let's go ahead and put that into the system. So we're gonna make our own functions up, make sure you save it before we screw it up. It hasn't been saved yet. Save it under.
It's already cooked too. No.
No, it looks like it's weird. That's maybe a Nepal.
What, the color?
Metropolitan.
Ice cream?
Chrysler.
I kind of made it up out of nothing, so.
It's a Chrysler.
Well, there's no engine, so it could.
Definitely a Lamborghini.
Oh, there you go. Okay, so, we all there? Let's go ahead and say model function. So here's our function that we're gonna put in, right? We're gonna try to see if this works. The type versus time. Now, we're gonna start at 0 with that sign. So the variable is equation. Variable is x. And we want to have delta t of 1,000th of a second. 0.0. Yeah, so that's delta x would be 0.001. That make sense? Cool. And we wanted to have that pulse duration equal between 0 and 0.051 seconds. That's going to be the duration of the pulse of that input. Does that make sense, everybody?
Okay.
Okay, so over here, y is going to be equal to, and if I've done this math right, multiply it through, it's going to be sine of 3,529, which should be 386.4 divided by 0.102. Okay, times,
What was it again?
3,529, times exclamation x. Remember that's the walk, exclamation x, close parenthesis.
Capital X?
Let's make it things out of there and make sure, lowercase. I don't think it makes a difference, but when I say that, it'll make a difference. So let's go ahead, let's say add. So there's my half sine pulse. Does that make sense? So if you think about it, that's gonna be
Oh, this is supposed to be
the force
0 to
displacement on the wheel.
0.05.
In particular, on the front wheel. because there's a time lag between the two, isn't there? Now, normally we put that as an analytical function time delay, but we're not gonna do that because that's not really supported as well. So that looks pretty good except for one thing. This is a very short duration, right? When it gets over to here, it will then take these last 2 points and extrapolate based on the last 2 points for the next time step. So we have to make sure that we make sure it goes to 0. So we're gonna say single value now. Here, go enter single value, and we're gonna say, say 0.1, doesn't really matter, 0.1. Equal to 0. That's gonna, no, I'm sorry, 0.1 here, and then equal 0 for y. Just put 0. That make sense? So we're gonna add another data point that says at 0.1 seconds, the value is equal to 0. Say add, and you can see what it just did then, right? It just added this on. So now if it extrapolates anywhere in this region, it's gonna get 0 input. So if I put this as the input, then it's gonna, and then 0 from the infinite. So that's like the front wheel going over a bump, and then that's it. Goes over the bump for 0.551 seconds, and so that looks pretty good. So we're gonna say, okay. So that's our first one. Now we're gonna put the second bump in, right? Now we're not gonna do anything fancy with time delaying. We're actually just going to do exactly the same thing, but we're gonna put a delay in it. So if it's gotta go 18 feet, now we're at 20 miles an hour, it's pretty easy calculation, right? And, oh, here it is. So 18 feet at 20 miles an hour takes 0.613 seconds. Make sense? So for the first, after analysis starts, nothing happens to the back wheel for 0.6 seconds. And you can, so now you can see how fast this is going over as well. So what we're gonna do is we're gonna say single value at 0 is 0. Say add. Okay, so that's gonna be our starting point. For the very same reason that we have to add zeros to the end. If you're looking at the back, and this is your back bump, it'll just extrapolate, so everything which should be 0 is not gonna be extrapolated out and be quick bumpers now. So we gotta say, okay, it's always gotta be load defined, so we're gonna make it 0 up to the beginning. Does that make sense, everybody?
You went from x equals 0 to 0?
Now, we started, we just say, it's a single value, so add 0 to 0. Does that make sense? Okay, so now we can put an equation in, and we're gonna offset this in time. So this one's gonna start at 0.613 seconds. And it's gonna go to 0.613 plus 0.051, right? So it's 0.613 plus 0.051 for 0.664 seconds. Oh, no, sorry, okay. So 2.664. And so this is gonna be equal to the sine of what we had before. We had 3529 times open paren. Ampersand, exclamation X minus 613, because we're shifting in time, right? 0.613.
How do you edit the function? If you edit it, right?
Hit add and see what happens. Oh, wait. Almost. Just say delete that, and delta t is 0.00.001. Right? Make sure it's 0.001, and it goes 0.613 to 0.664. Yeah. That look better? So that's what the second wheel sees. Yeah.
Can you write that bigger on the board? That.
This is the equation?
Yes.
Okay.
The time delay.
Very I'm gonna make, is this okay? I can erase this? I'll put it over here then. I'll make it big. So this is, the first one is 0, 0, right? That's our first data point. And the second data point is the delta t is equal to 0.001, right? And the time goes from 0.613, that's when
You're good.
it's the second bump. So now it's the start, right when the first wheel hits. 0.613, the same bump, the second wheel hits, correct? So the analysis starts with, I shouldn't say start, but the wheel sees it start at 0.613, and the total duration of that pulse is 51 seconds. So it goes to 0.664. Does that make sense? And what's the value? Now, what we've done, you can't just use those directly because we're actually just taking them and shifting in time. So it's going to be the sine. And we did actually make one mistake here. I apologize for that. But we can probably correct later on. We forgot to put the 6 inches in there. Right? Actually, I think we can modify that, or we can redo it, doesn't matter. It should say 6 times that. So it's going to be equal to our 3529. And again, 3529 is nothing more than our period inverse, which is frequency, times 360 degrees per revolution. 29 times, and we're going to shift this in time, exclamation x, that's our variable, minus our starting point, 0.613. Does that make sense? That's what the second wheel would see. I tell you what, let's not worry about 6 inches, let's just say it's a 1 inch bump. Kind of boring, I know. Nothing happens about the 6, the 1 inch bump, nothing like that. But there's one more thing we have to do, right? What's that? What else do we have to do? A zero value, otherwise we interpolate off of this guy, right? So now we're gonna say single value, and we're gonna say, basically say 0.8 or something like that, doesn't really matter. You could say 1,000, but then it's gonna be still big, right? 0, say add, and that's our bump. Now, of course, this is shorter than the analysis duration, right? That's okay, because it's just gonna extrapolate from the last 2 points, which is here and here. So it either interpolates in between or extrapolates. Does that make sense?
What's the point?
This one's going to show you, because this is the time delay of the 20 mile an hour. So say okay, cancel, save.
Where do we have the bump? Where do we have the bump?
So right now we define the displacement profile, right? That's all we've done.
I wasn't able to add the.
What's that?
I wasn't able to add the last one.
We're not. Single value. 1.8. 0. Okay.
Roger.
What?
See you later, man. Have a good day.
Thanks, man.
Okay, your business, bro. Thanks for my job interview next Friday. Good shit. You gonna call back from Niagara yet?
What?
You gonna call back from Niagara?
Definitely. When do you have yours again?
Tomorrow. Okay. But I have it at 8:15, but then I have an in-person interview at 8:30. I emailed her, so. I just think.
I'm
Be in the freaking parking lot, just interview.
Okay, so let's.
It's here, interviews here.
Go ahead and put this in now, right? So what we,
During the-
what we define then is two equations, and that's the profile
Pepsi
of the
Cola.
wheel going over the ball. Does that make sense? So what we do is we say, okay, I want the displacement of that wheel to go over that ball. Okay? So let's go ahead and do that. We're gonna say, model, load, nodal. Now this is a little bit different. There's one called enforced displacement, enforced motion. That can be used also, but that's using a large mass method. This is actually kind of cool. So we'll give it a name. And select the one wheel over here, doesn't matter which side, say okay. And this is going to be displacement in the x direction. Let's put 6 there. This is what you can actually multiply by 6 there. And it's going to be the first function. We can actually give it a name if you wanted to, like first, like front bump, second bump, or something. Before you say okay, is that okay for everybody?
Is it the first one because you clicked on the first letter?
Yes. It would have made sense to rename it like first bump and then rear bump or something, front bump, rear bump. Yeah,
Why is it in the X direction? It's going to the
you got a good point there. Excellent. Should be the Z direction.
Y direction.
That should be the Z direction. So, oh, the Y direction.
But C direction.
It's actually Y direction. Man, if I design airplanes, it'd be flying like this all day. Is that good? Okay. And let's do the back one now. That's a good thing about being a professor. Do whatever you want with no reason.
Tenure.
Yeah. So this would also be in the Y direction. 6 inches. And the time is a second.
Also, I finally got my reimbursement check from
And
Northrop.
we're gonna do exactly like we did last time.
$250.
Make sure. I'm not even gonna go through the dynamic analysis. So this says non-vertical to vertical. Nah. You can if you want to.
Now we're just running over a body on the right side now.
Yeah, because it's like swords out of the way.
Yeah, but you'll squish the body, so it won't be as big of a bump on the back one.
I ran over 2 bodies.
I mean, what if the front tire ran over the two bodies first?
I came in drifting, bro.
Students, it's okay.
But then again, it wouldn't be straight off the axis no more.
Do you know the worst bumps I've ever
Or-
seen?
I run over your face. Your body turns around. I run over the rest of your body.
Right.
How about a sidewalk?
Yeah, it's like, the rock is big, it's this big.
Is this supposed to truck going over?
I
No,
cloned
you do slow
Arturo.
down.
I put 2 Arturos.
That's what you do, because 4-inch bumps is gonna make a big semi. So it makes this big bump, but my little truck is like. Well, like half a mile. That's where you get this stuff in. Come on, bro. Hey, dump for me. Okay, so this is ready to run. Everybody there? Cool. Okay, let's try it. So we're gonna say file, export, analysis model, and then create.
Oh.
Go say delete, get rid of that guy. It's kind of confusing why I got the whole one. Transient, okay, good. Okay. And then we're gonna say,
Now we're going next this time?
yeah, oh yeah, we have to. We have to say, edit down here, and then say next. We have to next.
Next,
And
next,
then
next.
Next, next, yeah, next. Next, that's it, right? And then, let's put the same damping in, but I think let's use, instead of, so 0.05. And then for the, damping here, we put, I can't remember the frequency, it used to say 20 hertz. Number of time steps, now this is interesting, because we definitely want to get a good profile on that displacement. But that's a lot of output, right? So what I want to do is I want to run this thing for, let's see, 0.06. How about 2 seconds? I think it's a lot. 1 second, data? See if we can do it. So let's just see, because these are very, very limited resources. So if we do it 1,000 per second for 2 seconds, let's just try this. Put in 2,000. Time step is 0.001 for stability. But let's put out every 5 steps. So that's going to give us 400 time steps. We'll see if that works. Because this is an internal, but it only actually saves every 5. Does that make sense to everybody? Might crash. Okay, say next.
Cute, might crash.
Next. Next. Okay.
What? There's no steps right
3 fatal errors.
Oh,
3 for me.
I don't know if mine stopped running because you're almost out of memory to process.
Yeah, that's gonna be a big problem.
I had to close a few things. It just takes a while.
Yeah, this has got a lot of user freedom for these little computers.
Should be.
So you're still right away to 3 errors? Let's see what the errors say. Say show details. And then fatal, you just click on the, says here, your table D1. Oh, your table's bad, right? It says your table D1. For some reason, you have bad data on your table D1. Yeah. Is the plot okay?
It's model. Oh, I'd have to go edit, huh?
Yeah.
Edit, load.
Yeah. So if you're getting a table here, if you use a value that's less, so if you go here and then you ask for a single value anywhere beyond that, then it has to fall back. It won't work. It has to be a monotonic increase.
How do you edit the table?
You should be able to say edit it. Let's go edit and then table, the function.
Modify,
Edit,
function.
and then function, and then pick up the one you want.
Okay.
Okay. And that looks okay.
This
How
is
about
table 1, right?
It's table 1.
Can we check the other one?
Yeah. And then look at the table 2.
So on the other one, what I did was I didn't put 0.664. I put 0.051 plus whatever it was.
Oh,
So
so
I don't know
maybe
if that's the issue.
it could be. If I looked at the actual input file, I could tell you right away. So if you bring up the .NET file.
Yeah.
All right.
Is it
How do you
working?
reset this? Delete, reset. Okay.
Is it
I'll just,
working?
what is the?
0.664.
Is single value 00 first? This
Yeah.
is 2.
Yeah, so you want to delete.
Go to contour.
Let me see if I can find mine for you.
And
You
then
go to contour.
Second time verse, right?
0.664 was.
Based on,
Yeah.
The contour started to.
Oh, I'm almost
What was my
there.
delta?
Yeah.
What?
101.
No, total translation. Is that okay?
Okay. Ooh.
Nice.
Really, really strong body right there.
There's no suspension on here, right? So we're
Oh
actually
my
taking the whole body
goodness.
to do this. Normally you have a suspension on it.
This is
Pretty fun.
Why is the front so much worse than the rear?
It's probably just. It's just that much worse.
One, 6.
Back just
Oh,
kinda
what is it,
lifts up,
2?
The whole front end just like.
It was, point.
Professor,
Yes.
can you help me with my function reactions?
Yeah, so it takes this looping through, so you hit a bump and then.
This, oh, like, how do I?
No, I was gonna ask.
Oh, I know. I just got I mean, we're going to 20 miles an hour over a 6-inch bump.
Can
And a
you,
really flimsy panel. I mean, it's really, because there's no stiffeners in here at all, right? I mean, this is just sheet metal, all it is. So,
help me with my function, Professor?
Yeah.
Thank you, Damien.
How to start the analysis and then set up the analysis.
okay, y'all ready? Let's go file.
Auto
Export.
What was the number?
Analysis.
So it matters going through that menu instead.
versus time.
Oh no, we
Yeah,
Single value. 0.
zero.
Delete.
Equation.
Say new.
This is 0.01x sine 3529 times
Whatever. Oh, you're using that version.
x
Okay.
minus 0.63.
Uh-huh.
And then this is point.
Next.
Was it,
What is this?
I'm trying to think of a point 664 was. Let me just.
Was this the 2 value? Like was 0.6642?
And then here, put in,
Just wasting my memory on this. No, I'm just kidding. So,
And then
0, and then we did 0.613 to 0.664.
1.
So this one's
Now put 5.
0.613
That's what we did.
Yeah, that's the correct one.
Okay.
to 0.664
Is that-
of that guy.
001.
And then you're gonna do,
Because
good.
the reason why it's such a small time tell is because we want to get a good definition on that, of the input force. If we use, say, 0.1,
There we
then
go.
you'd only have 5 data points for the
Like,
half time set. So now we have 51 time steps.
we just took it there.
Again, I mean, we went over a 6-inch bump, a pretty nice sheet metal car,
If you run out of memory.
right? With very low down, very low down.
UI or Lumia?
Now, what's the time? Because normally you have lots of stiffeners in it, right? So, I mean, I wouldn't base your car on these results. It's just I wanted something to look like the car. You can imagine if you now extended this down to, real body, real
Bottom
car.
one's 5.
You can actually see that.
And that one
You actually see the car responding.
yeah.
Also, you notice this, there's a lot of force in
You
this,
did take a
in this
screenshot.
cross member over here. There's actually no stiffness in it. It's just a piece of sheet metal.
Professor.
That's pretty cool though. I mean, that's kind of what you see, but you wouldn't see it that bad. No question? Oh, what's it say?
Are we doing multi-set animation?
We only have one set, so.
Okay, animate.
So it's gonna immediately stop.
Oh my goodness gracious. Let's see some wigglies. No wigglies? Why are there no wigglies? Oh,
Pretty sure I'm just gonna pass out EGB tonight.
yeah. Oh, it's thinking.
Tired. My shit ain't working. I feel like you, bro. Shit.
It's not picking up the D though, it's all. So let me look at, go ahead and read about this for now. And let me look at your, look at your,
Yeah.
see the two functions. And,
Say,
It doesn't.
What is
doesn't-
FEA? Advanced FEA.
Mine finished.
Anyway, so what I'd like to do for the very last project is, right now, we're hard connected, we're moving those guys up.
He's doing the advanced.
What I'd like to do now is, instead of doing like this, I want you now to put in a suspension, anything you want. A vertical, and you can just, what I would do, I'll do it in all 2 directions, but make the 2 side directions. 2 horizontals, make them very stiff. And then the other one, the vertical one, make that around 500 pounds for the vertical.
There we go.
I mean, that's
Oh,
a big
right.
step for the shell.
It is very stiff, it's way too stiff, isn't it? So I think in a car, the unsprung is like almost twice, you probably get like 6 inches to front stirred. Unsprung is, and each one would have like maybe 500 pounds. Okay, 100 pounds per inch, right? So what would do 50 pounds per inch? Because you're right, this thing's so light. So go ahead, make a coincident node right here. So what you're gonna do, this shouldn't be too bad. Jesus Christ. It's all about having fun. See, right now, you have node right here, right? And that connects to the frame. Feel free to modify the car, whatever you want to do. So that, if you want to, sure. Right now, you connect to the frame here, to this point over here, and then we're putting the force motion right there. So this is fixed 1, 2, 3, correct? So what you want to do is you want to get rid of that constraint. I don't think it's a coincident node point right here on top of that, right? I'm gonna show it to be slightly off. And then you're gonna put 3 springs in between here and here.
Wow.
Make this one in the X. And gives the Y. Then make those between here and here. Make those like, 10,000.
V map, it would be the X and Z.
And that would be, X and Z. Yeah, so that would be, X and Z, right? So that would be like KX, KZ. That makes sense? And then make the vertical one, which would be KY. So KY, we said about 50. Does that make sense? And then constrain this one over here, 1, 2, 3. And then take that load you put up here and then put it down there.
If I put 50 in the V map, it'll automatically, because of all the units we're doing, it's already 50 pounds per inch, right?
50 pounds per inch, yeah. And then you can also, if you want, because one thing we don't have over here is the suspension shock absorbers. It doesn't really matter how that, you might want to put a vertical shock absorber in also. In which case, I would probably just make something up here. Let's just
So
say,
for part 2, when we started, what did we do? We just started doing the
Say 200.
functions, right?
Oh, no, you import your data, remember?
This is a tube, this is.
Oh, no, that was just part. No, but it was data. Sorry. Oh, yeah, your functions.
Now, per inch per second.
Show them the be here and then what we're doing for the project.
That makes
You could be
sense?
so lost.
So if we put in 200 as V map,
I'm done with him.
Because we're working in English units, that's 200 pounds per inch per second. Yes,
You know how that bump we applied it on that little corner thing?
yes,
Now apply it at the bottom.
yes, now put the load on the bottom.
No,
Put load on the section.
I mean, I was also told by like
So when you animate
a
this,
lot of
can you see
people
it
last
above
semester
first and
to
then
watch
Nobody
out for.
told me. Not even informed. I think them.
Professor, can you help me with the functions that were somehow wrong? So I just started over.
Okay,
It's
it's just the front of the back.
This would be it doesn't matter. I need to do
Okay.
both now. I just erased all.
So it would be
Equation was initial,
equation,
right?
yep,
And then,
001,
okay.
and then,
This would be
X,
0.
yep, and it'd be 0 to 0.051. Oh, not here. So 0 to 0.051, and this would be
Sine of
sine of
3529.
3529 times
X
exclamation
point X.
X.
Okay.
Just like that. Add.
All right, and then we had to do the
And then
single
add a single
value.
value, say,
0.1.
0.1 at 0.
Okay. That one's good.
Okay, good.
So the second one.
Okay,
The
second one.
starts at 0, 0,
Okay. Equation.
and then it would be,
This started at.
yeah, I think it's over here. It would be, starts at 0.631,
Okay.
goes to 0.664,
All right.
and the value is sine
3529
3529 times
parentheses
parentheses, exclamation X
minus
minus 0.631, close,
add.
add. Something's wrong. I think you didn't change delta X. Yeah, so I gotta just redo that, they delete it. What, did you make a full model? Make a full model. I mean, blow it up.
So you gotta do 0, 0, right? Yep. And then 0.6, 0.3, 7, 3529.
Is there a way to modify those?
Minus 0.613
Yeah. I think it's because
and delta X.
right now it's just
Is it 0.01?
So it would actually kind of cool to add some
There you go.
zeros in front. So it's driving up and see that.
0.8, 0.
What's that?
Okay, and now I gotta do my. I
So-
deleted my constraints or my loads.
Yeah.
Nodal.
26 seconds of that, yeah. You actually see it in front of the back.
I'm sure that's what I have to do for the model. So this is Fy
Don't forget this is displacement.
displacement
Six.
Now you remember, this is really being blown up a lot. You know.
First one.
Mention this function.
You forgot to define
So
them as
most of
time
the time,
functions.
you
Just go,
do-
no,
I swear I did.
just go to, modify. Edit.
Okay, I'm sorry, you got it?
Yeah, I forgot to change it to versus time.
There you go.
Oh, verse, yeah. Yeah, you have to verse.
But I did it the first time, so I don't know why. But now it still shows dimensionless functions. I'll rename them.
Any questions you know about this? This is
They're
more
not
like kind of
different.
fun, I think.
Is there a way to modify those, like, or do you have to redefine it? Put that to spring.
Wait.
Okay, and
Okay,
then
now your loads.
or
Yeah, like,
model
let's say I just want to transfer that
load.
mode to the new.
Oh,
Nodal.
See what happens.
You should be able to do that.
6 and Y.
Well, as long as you don't save, you're good.
Let's try it,
Bump.
so modify.
I think that's the way if it crashes, it won't save it.
Modify, edit,
6 in the Y.
load individual, and say, this is what we.
Now I'm ready to run, right?
Yeah, that seems about right.
It's on the node.
Well, I can just say, well, this is the, yeah, click on the node.
And it's next,
Now,
next.
you're gonna have to, but everything's defined, don't even define the function. Just delete that load and delete the new load. It's not giving you the option to change the location.
Oh, static, that's wrong.
And it's pretty easy, just, like I say, just delete that load, make a new load, same function stays the same. And just a different data point.
0.05.
Could you give me the transient damping ratios and stuff like that again with the steps? It was 0.05,
0.05.
20, and then what was the number of steps? 2000?
Yeah.
2000.001, output 5.
Okay. So I think we should be good. Find everything.
Now, one thing we might be able, this is interesting, I've never done it, so just out of curiosity, let's go, model,
But if you're not neutral, that's what
load, nodal. You click on any point, just see what works, click on any point you want.
Battery's about to die. Recharge
Except the
it.
point where we're gonna put it at. Okay? And then if we said, let's what if we give you a copy option? Sometimes we give you a copy option.
No. It'll tell you when it's done. all the outputs were kind of like it takes long.
No, I don't see it. See, the other option, which we could have done, which I think would have been a little more complicated, you could give you an option to put the phase lag in it. So we could have calculated the phase lag between the first and the second month. But I think that, the number thing would have been a little bit more difficult. Any questions on that?
You said you wanted that point below
No, it's gonna be coincident. I made it below because I made a coincident, you can see stuff. It's coincident.
along the car.
No, it's coincident. Exactly the same location.
What's the distance? Yeah,
This is here. What's that?
yeah, what's that distance?
It's coincident.
Okay, then,
Coincident.
They're on the
They're
same
talking to
spot.
each other.
Right here.
Coincident.
so what are the springs connected to
Here,
then?
Let me do this.
What are the springs connected
Okay, So
to?
this is what I'm doing. There's a string in between my two coincident points. Here's the first
It
point,
takes forever.
right?
to watch it.
Here's the
I
second
could
point,
like
and
5
here's the
minutes.
string in between. That's what you have, right?
Sure, sounds good.
But that means nothing, right?
Yeah.
So I separate these two so you can actually see the string.
Got it.
So we're doing it on map. Do we have it separated? Or do we have it on the same exact?
Coincident.
Exact single constant.
You have an infinitely small spring.
Yeah.
You have to like have them separate to be able to apply the springs and loads.
Well, the other words,
Right,
you
you know,
can
which
put,
one-
the other words, you can put the suspension in. Right, and then we're gonna put the load, the profile at the wheel. Look at you, doesn't make sense. It's just two coincident points.
And where do we connect the other one?
What's that?
Where do we connect the other one?
The other one, this one's already connected.
Yeah.
To the frame. This one will be connected to this one. Through 3 springs and 1 viscous damper.
So those two don't have any other endpoint?
What's that?
They're coincident.
They're all coincident to that guy.
They're
They're
yeah.
all
It's
coincident.
like we did in that transient problem.
They're all coincident. This guy goes to this one, X, Y, Z. Again, if I draw it like
Damien.
like this,
What are you gonna do for the lab report, dude?
I could do this.
I put in the, what's
Yeah, no, I can get it.
Got it now?
the theoretical frequencies. And I made,
Oh, you
like,
found how'd they match up?
they're all right. They're pretty good. A couple, like,
So we go
one was like a
activity, we
70%
keep
error, the other ones were
function,
like 20 or less.
That's all you're gonna do.
Yeah, it's fine.
Yeah,
We're working
It'll be fun.
we can talk about working with old machines.
yeah, yeah, yeah.
This is,
And stupid
kind of fun
students.
stuff to find home versus just running it and doing that.
And then,
Okay, so we
I
done?
made the schematic.
Go ahead
followers,
and, do you wanna save those
blocks
on
and
your,
stuff.
your
It's,
comment?
it's pretty ugly, but I mean.
Go ahead and save it.
Nice.
And I'm gonna talk a little bit about the
Like, not to
project
scale or
we're gonna
anything,
do.
but.
It's cool.
So we're all gonna do a project, individual projects, a group project.
You could do a group if you wanted
It's all
to.
gonna be modeling, but no solid model. You can't do any like, report models, anything like that. Everything has to be done using, stuff we've learned, right?
So this is our activity then.
Yeah, this activity.
Okay,
Hopefully it won't take you more than
5 minutes.
maybe 2
Arturo, probably 2 hours.
By now going.
You won't figure out how to do a coincident. Just kidding. Love you, Arturo.
Maybe it was not really coincident. Making a 1-inch apart.
Nice.
This one-
Still isn't done.
Takes
Jesus Christ.
Takes
Go
forever
ahead
to
and,
save too.
this is not- don't
You're
set
still
down
doing?
what's going on.
Mine's saving. I'm just trying to save.
So let me show you some kind of previous ones that we've had.
You wanna,
And again, I've been talking about for a while, so you can see that the dates are pretty old.
Real quick before we go,
Yes.
how did you get to do it only in one direction?
We load or what?
Spring.
Oh, because you DOF springs. Use DOF
Oh,
springs.
that's right.
Yeah, and then make sure when you do your DOF springs, they use different properties, right? Because one will be XX, Y to Y, and Z to Z. And remember, you can't do a viscous damper, even though it has locations for both of them, you can't do a viscous damper with a damper, with the springs. So do your springs and add a separate viscous damper. So when you get done, you're gonna have 12 springs and 4 dampers, right? So actually, what you can do is you can make the X the same property for all 4 locations, and then do the white string for all 4 locations, same property, right? And then do the Z for all 4 locations. So you only need 3 properties for the springs and 1 property for the system. Does that make sense? And definitely do, even though the load's on the one side, do the spring on the other side also. And
Can we-
then you can actually see the car walk on the suspension.
Mine looks more normal.
So there's a variety of, of what people have done. And the more complicated, and more sophisticated it is, the better,